So the point of this primer was actually to anticipate the voluminous number of graduate students that would be coming to these lectures, and therefore allow me to tell them a bunch of things that they need to know for tomorrow's lectures by Ido and Yoshi, so that Ido and Yoshi didn't have to cover Crystal Growth 101. So, how many students are we? Right. Okay, liar. All right, so it's redundant for at least 2 people in the room and probably others. Nonetheless, what this object is the focus of some interest to people. We heard this morning about what happens when molecules land on the surface of ice, at least in part, and this disorder in the surface having some influence on not only the equilibrium structure, but perhaps the growth structure. I'm not going to deal with anything complicated with respect to that, but I'll just note that the object under consideration is of interest for a whole variety of reasons, not just how it's different when the presence of an antifreeze protein, like we'll hear tomorrow, is near and or attached to the surface, but indeed just as a system in which pattern formation is rather nicely exhibited. And therefore, since there are generic patterns that form, they must have some generic origin with a marginal amount of system specificity. But in so studying things like this, which are ubiquitous, we also understand things that are relevant to any crystal growth setting. Okay. So it's that context. So I want to talk about generic things that happen when crystals grow, and that also happen really when ice grows. Okay, so I know that Ido has a better picture of this, but this is the time evolution here of an ice crystal growing under pressure into the liquid, and the liquid is supercooled. Okay, and so what I want you to notice is that it's a circle. Nearly, it's got a very small extent out of the page. And as it grows, the circle becomes this ramified crystal. Okay, so the circle grows for a while. This is the c-axis. This is the perpendicular to the c-axis. So the basal plane defines the direction, the plane perpendicular to the c-axis. But what you notice is that the circle becomes unstable, and this fingered structure appears. Okay, that's about 0.5 millimeter from here to there. Okay.
Yes.
Now,
interesting. You don't see any hexagonal symmetry.
Not yet. You eventually do. I'll just mention that momentarily. Mostly, I don't want to talk about this. That's the iconic. So from the vapor phase, you get these 6 arms, which have this dendritic structure. Okay, the mechanism responsible for this instability and of the circle becoming this fingered structure, and the mechanism responsible for this object, which I'm not going to call a circle, becoming ramified, is the same. That's basically a diffusive instability. And so if you're not familiar with it, think about the simplest system, which I just found out today. Yoshi is flying an experiment in the Japanese module of the International Space Station in November, which is basically this experiment. You would ask him why he has to go to space. And since he's here, you can ask him yourself. The reason is that the pattern would depend on the fact that there's a 4-degree density maximum. There could be convection. All right, so imagine that I've got a crystal growing from this pen, a crystal growing into a supercooled melt. Okay, so this is the solid, and this is the liquid. Okay, and let's just say, for the absolute simplest case, that this liquid is supercooled. Okay, so what determines the rate of motion of this interface is the diffusion of the latent heat produced at the interface into the melt, which is supercooled. Okay, so the dimensionless heat equation for the temperature is just del T is equal to Tt. Okay, so T is the dimensionless temperature. So it's just a Laplacian operator, and that means if this is 0, then all of the liquid in here is supercooled. Okay, and it's got a decay length scale that depends on the thermal diffusivity, which is not in this equation. It's scaled out. And the rate of motion of this interface depends on the flux in the liquid phase. Okay, and so I ask myself what happens if I perturb this interface. Okay, which is what the crystal is starting to do. It's starting to exploit what's called the point effect of diffusion. If it increases its surface area, it can increase the flux of heat away from it, and therefore increase its local growth rate. And so imagine now that I've perturbed this interface. So the crystal does that a little bit, and in consequence, right at this interface, I'm exaggerating, but the gradient is sharply steepened, right? And so this equation here, second order equation, has two boundary conditions. That T goes to some value far away, T infinity, okay? And that the temperature at the interface is equal to the melting temperature. Yeah?
You sound as if this would be true for any system. That is not only water, anything, land or whatever.
Everything.
Everything.
Yeah. In fact, this is if you take any solid and grow it into any supercooled melt or any supersaturated vapor, it has to go unstable. Okay.
Can you explain this graph again? The vertical.
This is just temperature.
The vertical.
One-dimensional temperature.
But you're also plotting the spatial extended
So this is one dimension. Okay. So I plotted the steady state planar solution to the heat equation.
So it's Z versus T.
That's right. And it's dimensionless, so 0 is there, so it was all supercooled before I bumped the interface.
Z versus T. So that's T on the horizontal?
Yeah. Above the freezing point, below the freezing point.
Yes.
Okay.
Right.
So before I perturbed the interface, it looked like this. And in consequence of me perturbing the interface and changing the curvature locally, I increased the heat flux away from the interface. Okay. But I'm not finished with this boundary condition. For the unperturbed interface, the temperature is equal to the melting temperature, 0 degrees, okay, which just happens to be 0 if I take ice, but it's the scale of 0 for everything else. But in fact, it's equal to, for the curved interface, it's 1 minus some number, which depends on the surface energy and the density of the latent heat of fusion. In fact, it's the surface tension divided by the density times latent heat of fusion times the curvature. Okay, and in the small slope approximation, that's just this perturbation, its second derivative with respect to x now. Okay, so now you see once I have this perturbation, I have to actually deal with a two-dimensional solution to the problem. But I don't want to solve it all. I just want to tell you those are two boundary conditions, but I have a moving boundary. So I need an additional condition, okay, which says that the interface moves at a speed v, okay, which depends on the flux of heat, that's dimensionless flux, at the interface.
So the kappa in the line before is also 1 then, yeah? That's the same thing.
No,
No. Kappa is the curvature.
TXX.
Right.
What is it?
TXX.
So what is this kappa then? Above?
I said it, I think, 3 times. Gamma is the surface tension divided by the density times the latent heat of fusion. And kappa is the curvature, which in the small slope approximation is just this disturbance, its second derivative with respect to the horizontal coordinate. Okay?
But what you predicted there is the change of the surface structure.
Yeah, the main thing I want to get across is that if there's a disturbance,
which means change of the surface.
yeah, that's right. If there's a fluctuation in the surface, a geometric fluctuation in the surface, all of these boundary conditions have to be satisfied. Still far away, nothing feels that perturbation. Right along the interface, the boundary condition says that the temperature depends on the curvature, okay, and that the local rate of motion depends on the flux, that is this gradient right here, okay. And so the effect is that there's an instability, and it always exists. A small particle which is convex into its melt has a lower melting temperature. Okay, so in fact, at this place the temperature is low. Okay, and by parity of reasoning, at this place and this place the temperature is high. Okay, so that means there will be a short through the solid phase, okay, which will tend to melt this back. Okay, that's competing with, so that's a stabilizing effect, and that's competing with the fact that this bump increases the surface area and enhances the flux locally, which wants to make the interface grow faster. Okay, and so there's a wavelength, which is the most unstable wavelength, if you look at the linear theory of this, and it's the geometric mean of thermal length scale and this length scale associated with the surface energy. The thermal length scale really is the thermal diffusivity divided by the velocity. Okay, this is interesting for many reasons, but the point is that this is a length scale which is much, much larger than this. This length scale is typically nanometers or tens of nanometers for most systems, and this length scale depends on the thermal diffusivity and the velocity. Okay. But one can show that this is an instability, diffusive instability, which occurs in every system. Okay. And the only ingredient that you require is that this either be supersaturated if it's a vapor, or supersaturated if it's a solution, or supercooled if it's a liquid. Okay. And generally speaking, this is called the Mullins Sakarica instability, named after Mullins and Sakarica, or diffusive instability. And you can go into great gory detail when you analyze this and ask yourself whether this mode is subcritical or supercritical and so forth. So there's a whole industry. But the point is that this and this are due to this general phenomenological process, which is a competition, like any instability, here between the stabilizing effect of surface energy and the destabilizing effect of the diffusion of heat or salt or any other rate limiting component.
So the entire physics really just lies in the surface physics and not at all in either of the two interiors.
No, the interior is this length scale, and the surface physics is this length scale.
But the heat equation, you're solving in both domains without any extra terms.
I could. I mean, you know, that's the. But to explain, I'm not solving the entire mathematical problem. I could solve the heat equation here. I could solve the heat equation here. The results is basically the same thing.
But there's no reaction term, is what I'm asking, in the heat equation as such.
There need be none. This is it.
Yeah.
This is the rate of generation of latent heat at the interface.
Yes.
Okay, and that rate, that's a flux of latent heat which has to be diffused into this region. Okay, if I solve the symmetric problem, in which I imagine the temperature here is at some low value in the solid, and the temperature here is at some high value in the liquid, and is moving from the top to the bottom, you still get an answer like this with a different cofactor. Okay, but the same things happen. It's just now I have another boundary condition up here. And then the flux jump, which really here is only the flux on one side, is the difference between two fluxes. And that'll change the scaling. But really is the diffusion field times the surface energy. And the surface energy is stabilizing and the diffusion field is destabilizing.
And don't you need at least another dimension, or can you do it in...
No, so the perturbation is in 2 dimensions. The base state is 1-dimensional, and as soon as I have a bump on here, I've got this coordinate as well. And so that's why I wrote the operator like that. Right. So so that's why this is here. But now you notice there's a difference between this picture and this picture. And those are the details. I'm not going to go into that because mostly what I want to talk about is something much more simple. Except for I will say the following, that people have for a long time said that snowflakes with this 6-fold symmetry are a result of a diffusive instability of a seed which is like a circle, like this. Okay? But look inside of this. There is no such circle that goes unstable. From the initial point of nucleation to the stage where these arms grow, you basically have a polygonal shape, which is hexagonal. Okay. So you actually go from something that's got some blob-like structure to a near spherical structure to a hexagon. Okay, and it's the hexagon that goes unstable. It's not the circle, okay, that goes unstable. And it's the hexagon which I want to focus on. How do you get from a nearly spherical seed to a hexagon? Okay. And that involves diffusion indirectly, but not in an important way directly. Okay. Let me just go back. Now I want to plunge down into the surface a little bit and ask, what about different surface structures? I'll just tell you that so here's ice and water. So if you go out here into Haga in the wintertime and it starts to freeze, okay, and you look very closely, what you would find is that the ice that you observe after it freezes over a little bit all has this same orientation as the page here, okay, with the c-axis pointing out at you. But if you look closely at one grow, you would see that it grows like a pancake, very fast in this direction and very slow out of the page. Okay, and that has to do with the surface structure, so the microscopic structure of the surface. So there are so-called faceted orientations and rough orientations. So this was brought up this morning, but this is a picture of those, and I'll come back to this in a little more detail. But a faceted orientation basically is one that's smooth on the molecular scale, and a rough orientation is one that's rough on the molecular scale. And I imagine that if I'm depositing material, say from the vapor or the liquid onto the surface, there's a much lower barrier to material attaching to this surface than there is to attaching to this surface. So we saw the simulations this morning of add molecules on graphite substrate wandering around trying to find themselves, okay, and bind together on the surface in clusters, okay. That would be more like an add molecule on a faceted surface. If the graphite was rough and had a hill and valley structure on the same scale as the water molecules, then a water molecule would adsorb on the surface and diffuse to a hole and be stuck in there. Okay. So now, a given crystal has both of these orientations present on its surface at any given time, and there are two aspects of this that are important. One is an equilibrium phase transition or surface phase transition called the roughing transition, and here it's seen in a simulation, and it basically the simulation does the following. It looks at the energetics of the surface. It starts at low temperature. At low temperature, there is a very little benefit you get from making an add molecule on the surface, okay, against the enthalpy associated with having to pull it out of this low energy site inside of the facet and lay it on the surface. But as the temperature rises, you get more out of the entropy of configuration, okay, against the enthalpy of formation of the surface, and the surface then will undergo a transition which makes it molecularly rough, or atomically rough in this case. Okay? And the signature for that is that the height-height correlation function diverges. It diverges at a transition at a particular temperature, and the divergence makes the system look like this cartoon that I drew here. Okay? So that happens only if you take this surface, say at 0 temperature, and increase the temperature slowly. It will go through a transition where this configuration will prevail. Okay. So that's at equilibrium. You just imagine it's in coexistence with the vapor, and I'm sliding along the sublimation line until, boom, before I get to the melting point, the surface roughens. Okay. Sorry?
What was the order parameter for the transition?
That's the strength of nearest neighbor bonds.
Okay.
So people have traditionally studied this in helium. In particular, helium in this solid helium in contact with superfluid. And the reason is simply that what's not normally appreciated by people when they see crystals, either stones in the environment or crystals growing in the lake, is that they're very rarely equilibrium phenomenon. Right? You very rarely see an equilibrium crystal. You either see a crystal that was at one time strongly in disequilibrium and then removed from the ability to equilibrate and is in a kind of infinite metastability, or you see something growing. And the reason people study helium is because it's in contact with this material, and this material has nearly infinite thermal conductivity, zero or nearly zero latent heat of fusion, and so you can look at equilibrium shapes. Okay, so what you see here is as the temperature goes from low to high temperatures, the various facets of a crystal go through the roughening transitions. Okay, so at low temperatures, crystals in equilibrium with their bulk parent phases are polygonal and faceted on the molecular scale. And as the temperature rises, the various orientations go through the roughening transitions, and it becomes rough. Okay? Again, that's just simply changing the place you are in coexistence. And what I want to do is take then the crystal, the crystals we're interested in are ice, but any crystal slightly away from equilibrium, and ask what happens to the shape. One way to do this is using a high pressure apparatus to study ice in contact with water. And I just want to show you the same sort of sequence. You saw this in helium as a function of temperature. In the case of ice, the coexistence between the liquid phase and the solid phase has got this negative slope because ice floats on water. Okay? And the studies of Minoru Maruyama are a beautiful example of seeing the roughening transition, and he can move up and down this line, and what he observes is that there's a roughening transition of this facet, the prism orientation of ice, at about minus 16 and 16.5 165 megapascals right there. Okay. So just by moving along coexistence from low temperature to high, you see the disappearance of this facet. Okay. Again, the importance of that is that the way in which this interface grows depends on its molecular structure. Okay. If it's at this temperature and pressure, then there is a rough surface. It's at this temperature and pressure, then it's molecularly smooth, and you need to activate growth on the surface. I should just mention that the apparatus that he uses is, well, many apparati that he uses all are based around the original idea of Bridgman. And Bridgman invented high-pressure apparatus, interestingly enough, to search for a critical point up here between water and ice. So there's a well-known critical point that was studied by van der Waals, and the great success of the van der Waals theory, between liquid and vapor, right? So way over there on the right. And Planck wrote a paper which predicted that there exists a critical point here. Okay? And so Bridgman developed his high-pressure apparatus to look for it, and all he found was that there are structural phase transitions amongst various types of ice. Okay, so no critical point exists. Even Planck could be wrong. And what Bridgman found, and what others have since then, is that as you increase the pressure and lower the temperature, you get various structural phase transitions between different crystallographic structures of ice. Okay. So, we need to start from equilibrium. So what's equilibrium? I'll just remind you that because we have to deal with the surface energy, the internal energy of the system has the usual structure, where mu is the chemical potential, but now there's an introduction of a surface energy, which is extensive with the area. Okay, so there's a new pair of canonically conjugate variables here associated with the important role of the surface energy. Okay, and there could be an external field, phi. It could be gravity, it could be electric field, it could be any number of things, but that has to go into the system. And when you look at the variational problem for what's the shape that minimizes the total surface energy, you get a result. I'll come back to that in a moment, but you get this particularly useful result, which is called the Gibbs-Thompson-Herring condition. It has a reminiscence to this. So, as Alan said, this is the Gibbs-Thompson effect, the shift associated with the curvature of the surface. This is also the curvature of the surface. But the delta mu here is the difference between the chemical potential of the bulk system and the chemical potential right at the surface. And this is the molecular volume, and this is the surface energy, and this is how the surface energy varies with the second derivative of the orientation that defines the surface. Okay. And the important thing about the Gibbs-Thompson-Herring condition is that delta mu is invariant along an equilibrium shape, which means that the product of this and this as they move around on an equilibrium shape has to be a constant. Okay? So as the surface energy changes as you move around the surface, because I'm interacting with various orientations of the underlying crystal, then so too must the curvature. Okay? Correspondingly, to maintain this at a constant. So here are some images from some wonderful experiments done some time ago by Ayrault and Matois of lead, which is annealing on a graphite substrate. And you can see the facets peeking their way out. And the point is that as you move around on the surface in equilibrium, this product has to be constant. Now the first term, just for clarity, this term is the binding energy. You can think about it as or the energy, the irreversible energy associated with preparing the surface, okay, cutting the certain number of bonds per unit area. The other one is the work it would take to tilt the surface against the underlying potential of the crystal below it. Okay, and both of those things are important. Normally, we only have the first term, as it turns out. Okay, and this, if you're not familiar, this expression comes when I expand the chemical potential in temperature and pressure, and at a constant pressure I get this expression. Okay.
So the main thing in the plot on the right is that it becomes flat and bulges, that the curvature changes at the bottom, or what are the main points that we should watch out for here?
The main points are that is that as you move around the surface, you have flat regions and rough regions. That's the main point.
And also, I guess that also argues that with that Gibbs-Holm Thomson-Herring representation, you would never get completely flat surfaces unless you were right at Thomson zero. Is that true?
No, you can get a singularity in gamma
Singularity
tilde.
in gamma.
Yeah. In fact, facets are defined by low index orientation such that there's a singularity in gamma plus gamma prime prime. Yeah. But the point is that just to imagine yourself moving around the surface, okay, and some close associate of yours says, this is a low index surface and the surface energy as a function of orientation is 17.78 millijoules per square meter, okay, and you look it up and you say, okay, there it is, and they give you the plot as a function of orientation, and you calculate this, okay, and then you know what the chemical potential of the bulk is here, and it tells you that the curvature must be a certain value, okay, and this is a different way of looking at exactly the same thing, and this is the way in which people get the surface energy as a function of orientation for their crystal. They make the crystal, and then they wait. Okay, and that's the reason you would want to do helium, because you don't have to wait very long. Okay, because it grows a little bit, and all the latent heat is dissipated instantaneously. Okay, and then you look at it and you say you're in coexistence because you know the phase diagram, and you wait, and you look at the shape, and you say, okay, now I know the surface energy. Same thing here, and this is a different representation of it. I'll just go to the next version. It's the same thing. So the equilibrium shape comes from something called the Wolf construction, another interesting error in the literature. In fact, this paper, if you look at it, is really studying growth shapes. Okay, but Wolf put forth the idea, which is proper, that is that the shape which minimizes the total surface energy for the volume contained is the equilibrium shape. Okay. So in 2 dimensions, that's this thing. The minimum of IS, the minimum of the integral of the surface energy for the area contained, is the Wolf shape or the equilibrium shape. Okay. Now that's this picture. Okay. So what is it? If someone comes up to you on the street and gives you gamma as a function of orientation, okay, they might charge you a little bit and say, here's gamma as a function of orientation for this crystal, and you plot it in a polar plot, okay? So that's this curve, okay? And the Wolf construction is giving you this crystal. This is the equilibrium crystal, this inner line here. Okay? So the way to write it explicitly is shown here. So it's the set of all points R, drawn out like this, such that the inner product of R and the normal to the surface at that R has to be less than or equal to the surface energy times some Lagrange parameter. And that Lagrange parameter is the volume. In this case, it's the area. Okay? So the first picture here is just a picture of the construction. Okay, I pick my R, okay, I dot it into the normal, okay, and it has to be less than or equal to some value, and I take the inner envelope of all of those perpendiculars, and that gives me this shape here. Okay. So the principal important point about this is that an equilibrium shape can have facets, which are associated with these cusps, and rough orientations. Okay. And I want to know, that's my starting point, so I want to start with that and ask how that grows. Similarly, if someone comes up to you on the street and gives you, how does the velocity very near equilibrium of my solid-liquid interface depend on the normal of the surface? Okay? Then I can make a similar construction, which is called the Frank-Chernoff construction. Okay? Which is, instead of being on the surface energy, it's on the velocity. Okay? So this is a weakly disequilibrium statement. This is actually what Wolf meant. Or this is what Wolf meant, this is what he said. Okay. So, how do you grow such a system very near equilibrium? Well, the first thing you do is to call Minoru and say, Minoru, how do you grow such a system near equilibrium? And he says, oh, you put it in my high pressure apparatus. Here is just the upper right hand quadrant of a crystal of carbon tetrachloride growing into its melt. And it's equilibrium here, so remember this previous shot, so this is the upper right hand quadrant. Okay? He knows the phase diagram, he controls the pressure and the temperature, and so this is the equilibrium shape. I'm going to point out that you have all orientations on the surface between 0 and pi over 2, okay, on the initial equilibrium shape. Now I'm going to grow this and ask what happens. Well, you know what happens. There's two orientations, 0 and pi over 2. Okay. So if the guy who gives you the velocity function on the street says, here's the equilibrium shape, here is the shape after some time, how does it get there? And the way in which it gets there depends crucially on the way in which molecules attach to the surface. Okay. That orientation is molecularly rough. These orientations are molecularly smooth. So you already know that there must be very little activation barrier to it fitting a molecule into a rough orientation, but there will be an activation barrier to growing this normal to itself, because as we saw in the simulations of add water on graphite, they have to come together, they have to create a two-dimensional island, and in order to do that, you have to get enough of them there, and there's a Boltzmann factor associated with that. It's an activated growth process. So growth here is by adding monolayers through an activation process. Growth here is just like growing a droplet from the vapor phase. A molecule comes down and it sticks to the surface. Another one comes down and it sticks to the surface, and the surface moves normal to itself. Okay? So those are the physical processes, but now you know you have all orientations between 0 and pi over 2. Here you have 0 and pi over 2. There's two ways you can get there. One way is that you can maintain every orientation between 0 and pi over 2 up to the last second, and then add the last molecule onto the corner, and then you lose everything in between it. And the other is that at some intermediate place, you have losses in surface orientation. So this is such a case, and it turns out to be generic, and you can prove it. So the point is that after some time, you see corners forming. Okay. So they're discontinuities, which means I lost all the orientations between one orientation and the other in two places. Okay. So the answer is that it happens the second way.
Is there any physical significance to the experimental, that graying fringe in the top left corner and the lack of it in the bottom right?
Top left corner.
Well,
top right corner.
Well, top left corner. The interface has some sort of like diffuse look to it, and that's gone by the time you get.
Yeah, right. Well, there's the. I mean, if you had sharper eyes, you would have found the bigger flaws. But I was wondering what. I mean, I mean, here, for example. Yeah. Or even here. So this is an axisymmetric crystal. Okay. So there's still some of the third dimension. So what you're seeing is a little change in slope associated with the third dimension. Okay. So quantitatively, because there's three dimensions, you get a little bit of difference. But let me show you how small that is. I'll just say this is the setup for ice. It's the same kind of thing. It's a pressure anvil cell. Minoru has developed two of them. One, he can independently control temperature and pressure, and the other is he fixes the temperature and can vary the pressure. Okay, so he's varying delta mu, the growth drive. Okay. So in the case of ice, so now I'm just looking at a similar experiment, but now it's ice. Okay, and what you see is a polygonalization. Okay, so this is a dynamic shape, and the point is that the fast-growing orientations are lost to the surface. Okay. So again, in this simple picture, these are rough, these are molecularly smooth, these are fast-growing because there's no activation barrier to growth, and they grow out of existence, leaving behind the slow orientations on the surface, it's generic, and you see that a crystal growing of ice looking down the z-axis becomes fully faceted.
And this is for fixed delta mu.
That's for fixed delta mu. Delta mu on KT for these experiments is 10 to the minus 7. Okay, so that's the beauty of this apparatus, is that you can, there's this big flywheel, and you can vary the pressure, and you're just varying delta mu, right? And so it's got that kind of an accuracy.
If you wanted to grow a square or a triangle, would that be possible?
Not for ice. So for carbon tetrachloride, this is a square.
Yeah.
Okay. So shape. This is the equilibrium shape. It's a square with rounded off corners. When I grew it, the rough corners grew out of existence and created a square. This is just the upper right-hand quadrant of it. So the symmetry depends on the underlying crystal.
And if you just let that sit for a long time, you would eventually lose your facets.
Right. So that's right. In the case of helium, it takes a few seconds, and in the case of ice, so you drop the pressure and you go into the solid region of the phase diagram, and the ice grows, and as it grows, it polygonalizes, okay? And then you go back up to equilibrium, and you wait, and it roughens again, or becomes partly rough.
All these pictures, they're with the same size, 7.5 millimeters.
That's right, yeah. Okay, so things polygonalize during growth, and the way in which we model these things is using what's called geometric models or geometric theories. The crucial ingredient of these is that what controls the motion of the interface is the kinetics associated with molecules attaching on the surface. Okay? It is true that diffusion delivers those molecules to the surface. Okay? Because I've changed delta mu, it means that the stable phase is the solid phase, so material must go to the solid phase from the nutrient phase, whatever it happens to be. But the diffusion field itself doesn't control the shape of the interface. So whereas in this case, the diffusion field was essential in controlling the geometry of the interface, okay? The length scale of the diffusion field is enormous relative to the size of the system. You can think about it that way. Or the mean free path in the vapor is very large relative to the size of the crystal, okay? So that while material will go to the surface, the geometry of the surface doesn't depend itself on the length scales intrinsic to the diffusion field. It just depends on how the molecules attach and where they land on the surface. Okay. And basically, the way in which we think about this is as a string. So there's a string that defines the shape of the crystal at one time, and it's got a certain amount of total arc length. And at another time, it's got a larger arc length. Okay, it's just that the string itself has a motion that is highly constrained by the underlying microscopic architecture of the crystal. Okay. So that's this picture. I imagine, since I know the equilibrium shape, and I know where the facets and the rough orientations are, and I know how to keep track of orientations on the surface, that here's a piece of the surface. Okay, it has a unit tangent and a unit normal, which I chose to point inward. Okay, and the angle which defines the tangent is theta with respect to the positive x-axis. And I imagine in 2 dimensions I have this 2 vector which defines a point on the surface. Okay. And I want to parameterize it in terms of the angle which defines the normal there, or the tangent there. Same thing up to pi on 2. And it's simple. The interface just evolves in time depending on what the velocity is at a given point. Okay. How do I know the velocity? Well, the physics of how molecules attach to the surface, merging out of the equilibrium shape, emerging out of the surface energy as a function of orientation, tells me how the velocity depends on orientation. Okay. Rough orientations, you can imagine, as fast. faceted orientations, it's slow. So I have to update the surface as a function of time. My string gets bigger. I have to go to every orientation and ask how to move normal to itself. Okay. So this is the equilibrium shape we saw before. Remember, I constructed the equilibrium shape through the Wolf construction. So it comes from the surface energy as a function of orientation. And imagine now I've got ice, like the ice I've seen. So this pedal plot here is the velocity as a function of orientation. As we saw, the shape polygonalized and left the slow-growing orientations behind. Those are all the cusps that go very slow relative to the rough orientations. Okay. But as I move from a cusp or a facet to a rough orientation, I'm going from a region on the surface which is smooth to a kind of visceral orientation to a rough orientation. Okay? So as I go from this place to this place, the mechanism by which the growth occurs normally to the surface is a lot different. Generally speaking, it's just fast here because if molecules attach to a rough surface, it moves normal to itself. Here it's activated and very slow. Okay. So you imagine that it's just a homogenization as a function of angle. And so I have a function, C, which takes me from faceted orientations to rough orientations. Okay. And that function simply has the symmetry required by the crystal, okay, and in the lowest order symmetry required by the crystal.
John, I have a question. So when you go in between, you have some orientation in between,
Yeah.
and you make it steps. So this orientation does not exist, or you call this average orientation.
Okay, a couple of things. So I have a facet over here. I have the equilibrium shape, right? So my pictures are all drawing through this surface, okay? Informed by the microscopics, but not resolving the microscopics. So that's important. So over here, there's an orientation. And in fact, in the visceral region, this is the same orientation as this, and this is the same orientation as this, and this is, okay, and this is, and so forth.
But
Okay.
eventually you lose it.
But eventually I lose it in the corner, right? And so,
What's on the axis in that array? Only in the triangle. The horizon axis in that curve.
the horizontal axis.
Yeah.
So I'm just drawing the upper right-hand quadrant of, say, this crystal here. Okay, so I'm going from this molecularly smooth region over here to the rough region. And what Ido is saying is that this is all one orientation, and if I could blow this up right here, the distance between these steps becomes smaller and smaller and smaller, but there's still an orientation that's maintained, okay, until it gets lost into the corner. Okay. But the point is that we treat this as a continuous change from a very slow velocity, where I have to get birth and spreading of monolayers, an activated process, to a very fast process. But in fact, in this region, we also deal with it in this pedal plot by realizing that in this system, as an atom molecule hits the surface, it diffuses to the nearest step. And in one dimension, steps are always rough, because there's zero melting temperature in one dimension. That's the Pidal's result. So that's why molecules go to the edge, okay? And they do that. And in fact, there's something called Schwebel barriers, which deal with the energetics of a molecule when it gets near this edge. And as it turns out, all of those things can be simply dealt with here. Okay. And so the point is that no matter how hideously nonlinear my evolution equation is, although it looks tame, I can solve it by characteristics. Okay. So the method of characteristics gives me the evolution of the surface from the initial state, okay, and it just has these two contributions, one in the normal, one in the tangential direction as a function of time. Okay, so for growth, this is very technical. I just won't go into it. I'll just say that shocks form. Okay, that's these losses in surface orientation, which I showed you. Okay, and they also form. Shocks also form in the melting case. In the melting case, you can see that these characteristics are headed towards each other. If two characteristics collide, then they lose all the orientations between those two. Okay, and I'll come back. So you can evolve these shocks, and you see the shocks forming here and here. Okay, you can evolve them with this equation, and you can study how they depend on the microscopic model that you use for the velocity. But let me come back to that in a much simpler context. Okay. And I'll just note for you that there's an interesting difference, which we were talking about right before lunch, between melting and growth, or evaporation and growth. So here's a shape that I begin to melt. Okay, and let's look at. So now all I have are these pictures. So if you're given these pictures and locked in a room and asked to tell someone where are the crystallographic axes of this crystal, okay, I know if I'm that these are the A axes. Okay, the C axis comes out. Okay, but I would have to be told that unless I had some other information. I would have to have some microscopic information. If I ask what happens to this shape as it melts, just look at these facets. Okay, after some time, facets still maintained. All the corners are gone. Okay. And now it looks like this facet here has rotated 30 degrees. So now I see what look like linear regions, and so these corners emerged out of these facets. Okay. If I grow it again, back here, it rotates back again. Okay. So if you're just given that picture, and you know something about ice, you might say, well, these are the A-axes, or you might say these are the A-axes. Okay. You probably always say the C-axis came out, but importantly, with this picture alone, you don't know enough. You have to know how close is it to equilibrium, for example. So what happens in growth is that the fast-growing orientations are lost from the surface, so this is growth, and leaving behind the slow orientations, these three prism planes. Okay. And in melting, there's a symmetry or an asymmetry, depending on your perspective or definition of asymmetry. In melting, the most unstable regions of the crystal are the corners. Right? So as soon as I change delta mu just slightly, the corner molecules are the first ones to go away, which exposes two more corners. Okay? And this facet starts to erode away from the corners, from all of its corners, inward. Okay? And there you see it. And there you see it, moving inward. And so the corners, which were the fast-growing orientations, are also the fast-melting orientations. Okay? And they erode away, and the center of facets are left behind. Okay? So the slow-melting orientations are left behind as well, because it's hard to dig in to the surface and pull out material from the facet. It melts in from the periphery. So it appears as though this thing rotates by 30 degrees, but it doesn't. So the message of this is that the surface matters, okay, in particular. So let me just mention briefly this business with shocks. It turns out that rather than using this 2 vector to describe the surface, I can redefine the evolution of the curvature of the surface. And it's just a fortuitous consequence of the combination of a number of things. One is the structure of the Frenet equations in 2 dimensions, which relate the evolution of the tangent and the normal to the curvature. Okay, and the way in which I parameterize the surface. And when I parameterize the curvature of the surface using the angle which defines the normal and the time, then I get a very simple equation which relates the curvature to the velocity plus its second derivative with respect to orientation, which is like the gamma plus gamma prime prime. And you can just write down the solution. Okay? So V tilde is just this. So you can imagine that if this is negative, if V tilde is for some orientations negative, and I showed you on this pedal plot of velocity that it can be, that there can be a finite time curvature divergence. Okay, so in some finite time, which is 1 over k naught V tilde, the curvature will diverge. And so that divergence, it turns out, is always saved. And you can prove for a whole class of geometric models of velocity that the shocks form before the curvature diverges. Okay? For any class of velocity such that the initial condition is a wolf shape, that is a convex shape. Whereas in other regions of the surface, the curvature behaves in a tame way.
So is V tilde negative, or is there a minus sign?
No, so V tilde can have any sign, positive, negative, or zero. Okay. So the point is that for orientation, so you make your model based on how the molecules attach and so forth. You plot the pedal plot, and there are large regions where V tilde are negative.
Yeah.
Okay.
So time is 1 minus 1 over here.
Well, no. For regions where V tilde is negative, the divergence time is 1 over k naught V tilde. Okay, because it's where V tilde is negative. Mod V tilde. Okay. Fine. But the point is that V tilde can be negative, so yeah, you're right. So for 1 over k naught mod V tilde. So you can plot that and find the places where you expect the divergence to occur. Okay, and you can say precisely what that time is for your model. You can go to the 2-vector description and say when do the shocks occur. And if you do it numerically, you convince yourself that you never get something going like this on the surface, right? No instability like this. And then it turns out you can then prove for all convex initial shapes that the shock time always saves the surface. I should just say that at large time, right, as t gets very large, then the curvature is 1 on V tilde t. Okay? So that turns out to be, so then move it to the other hand side. So the product, so let's look at that. So the product, kappa, V tilde, is 1 over time. Okay? So what does that look like? That looks like Gibbs-Thompson Herring. Okay? Up to, obviously it's cosmetic, but the point is that on an equilibrium shape, on a steady state shape, the product of V tilde times the curvature is a constant at a given time. Okay. So you have to go at a given time, you take a snapshot of the picture and you go around, this has to be a constant. Okay. So that has been used for a long time to analyze the growth of crystals, and it turns out that the long time limit of that equation is not asymptotic for all orientations. So that's the point of proving for any initial value problem that the shocks preempt the curvature divergence. So this is not valid for all orientations, because for what you said, you can't have negative time. Okay, this is technical. Well, in melting, geometric models get better as a function of time, just simply because the size of the system gets small. And in growth, they start to break down. If you think about it in terms of solutes, if I'm growing here, very slow relative to growing here, from an impure melt, I'm always rejecting some of the impurities, but because this is growing much more slowly, it's harder to get an impurity in here than it is in here. Okay? So there could be a gradient in the impurity concentration, which changes the local diffusion field, which makes these geometric models break down. Right, I've already said all this stuff. Anyhow, this is just the upshot is what I've already said. It matters what the surface structure is like. Crystals go very fast in the rough orientations, very slow in the molecularly smooth orientations. Anisotropy of crystals comes from the surface structure, certainly when they're early in their lifetime, and as long as they're not growing extremely rapidly, such that these diffusive instabilities become important. But this message is important, that is that the seed of a snowflake goes through polygonalization before it goes through the instability. And so once it becomes fully faceted and hexagonal, then these corners look farther into the diffusion field. That sets the stage for the six-fold symmetry of a snowflake. Those corners are reaching farther into the diffusion field. It's not the other way around. It's not that a circle becomes unstable to some anisotropic diffusion field.
And the other thing is that the difference with the Mons and Superca is that then the wavelength of the instability is actually not set by curvature effects in some sense.
Oh,
or
okay.
is it
Yeah,
the
so
size of the crystal at which point this diffusive instability takes place indirectly the link with curvature?
No, it's close. So the cheat, the way in which people try to do this is to say they recognize the equilibrium shape, and they say, it's true, so embedded in this is, well, this is equal to gamma of theta rho SQM. Okay? And then they say, ice has got six-fold symmetry. Okay? So let me impose that on gamma. Okay? And then they take a circle, okay, and there will be mode restriction, okay, depending on the symmetry I impose here. So you can get snowflakes from a Mohn-Szekeres instability of a circle or a sphere by imposition of a six-fold anisotropy in gamma, because you're imposing where this can be effective and where it can't be effective. But to leading order, one would say, well, just look at the crystals themselves.
Yeah, well, I guess what I'm asking is the internal seed from which...
No.
Okay.
Yeah.
Can I ask you a different question? Probably just Alan's reword. The original shape you showed had some size before the branches went dendritic.
Yeah.
How do you go between Mullins and Kirka giving you those dendritic branches and this giving you the initial seed having that?
Well, just think to leading order, the size of the crystal relative to the mean free path or the diffusion path in the vapor. Okay, so now you have to you do have to do the initial value problem, but you have to have the shape. Okay, so the easy thing about doing Mohn-Szekeres and imposing the six-fold anisotropy is that the circle is easier than the hexagon. Okay. So actually what Etsuro Yokoyama did on his thesis was in part to take a hexagonal shape, okay, and do a hybrid between these two things. You didn't actually do one or the other. But that's what you would do is then solve the full diffusion equations for that initial value problem, and ask under whatever conditions you have, does it become unstable? But if you see, the point is going through all this rigmarole is to say that all what I spoke about is extremely simple and easy to compare with very nice, pure, clean experiments. But what happens is that all this becomes very well changed when you put in antifreeze proteins, which is what these gentlemen have been working on. And importantly, as I would tell my students, you have to understand the simple problem before you understand the complex problem. These guys understand the simple problem. I don't understand the complex problem. These are the people I work with on these things. Andy is my student who may never finish his PhD, and Yoshi finished his PhD, and so did Minoru, and so did Michael, and so did Vadim. So if you know, so does it happen between here and there? That's the question that you would have to ask. My main point is that you get a polygonalization before you get a Mullen-Scarab instability. You didn't finish your PhD yet.
I did. So there's a pattern inside this area.
Yeah.
I was curious if you.
Of course, I don't know. I haven't known this crystal for very long. This could be the fact that it was melted against the plate against which the photograph was taken.
I just have saw that it might was got, because you don't know what the history of this thing, so it might get unstable when it was smaller, then get to some time to stabilize again, and then continue. You don't know the history.
No. But I do know that was that particular crystal was sitting on substrate. So my leading order answer to what this little blobby thing is that
no, I'm not
melted.
asking about that.
Oh.
I'm asking about in this regime between the two hexagons.
Between here and here.
Yeah, right. So on the corners you have some pattern inside.
Yeah.
You see, I don't have the pointer to.
Yeah, there.
This one. Yeah. Yeah. No, this is probably not Photoshop. This is look like something that left behind some kind of dendritic growth.
Oh, I don't believe that. But
Okay.
I mean, it could be. Yeah.
I don't know either. But
It could be.
But it's not necessarily a given size that was started.
It's never good to argue over the subtle features of someone else's photograph.
Right.
So it's like the same structure in the corners of the inner segment.
Here.
I think from here.
There.
So it could be stages. That it's not necessarily a given size. It's break off.
I think the important thing to notice is that note is that in what I think about and in the laboratory, delta mu is controlled. In the real environment, delta mu is a function of space and time.
Yeah.
So the idea of features that appear in some punctuated way being connected to something intrinsic versus something enforcing is, I don't know, maybe Yoshi should say something. I agree.
So how do you three-dimensional structure, so that is the surface of time. So
Yeah, I mean, there's
the inside the crystal.
Yeah, I should say everything I've been telling you it lives in 2 dimensions, and is not relevant to, certainly not relevant to all these patterns. But.
So I will want to touch on one thing that you said, that the theory becomes better when it's smaller.
Yeah.
So So I know that the crystal becomes sharper. Is this one-to-one thing? Because when I melting things,
Yeah.
I see sharper shapes when they're small.
Yeah, but you have to be careful. You have to ask yourself where you started on the phase diagram. So if you, so in the same way, if you start, we can go back to the very beginning of this. If we look at the phase diagram, right. So it matters whether you start below the roughening transition, and therefore you have this shape, or at the roughening, or at temperatures below. So where it's faceted. So if I take this shape, or this shape, which has got very weak facets underlying it, and I grow it, as I've showed, it becomes polygonal. Okay? So that very much depends on the initial value problem. So the partially faceted shape becomes fully faceted away from equilibrium. Now, if you were starting with a partially faceted or an unfaceted shape, okay, and you're melting it, then it still knows it's a crystal, right? So it still knows that the energy depends on orientation, and so it will become more sharp as it goes through its melt sequence. So that was this. It becomes more sharp during melt and during growth. So there's a melt shape. There's a growth shape. So the anisotropy is coming out of the system when it's away from equilibrium. So if you have a shape that's partially faceted or even under the optical microscope not entirely, maybe it's rounded, if you melt it or grow it, it will become more polygonal. I mean, I think that was my message. Now, whether the model that you use improves during melting versus growth is another matter. But the basic message of that is that the finite size, the size of the system matters for diffusion. Okay, the size of the system does not matter for molecularly driven growth. It only cares where the molecule lands on the surface and what that surface structure is. Whereas diffusion cares about size. And so when the crystal is getting smaller and smaller, then it's getting small relative to the diffusion length in some sense. That's a loose statement. But what we did was analyze what happens when you put in the diffusion field very near perturbation, where you have two orientations. And you can see that you get a buildup of heat in the simple case, which diffuses from one place of the surface to the next, which locally changes delta mu, which locally changes the shape. And as the thing gets smaller, that gets better. Okay, now you know everything.
So how about the other parts of the crystal, which don't grow like a hexagon, of course, they form the beautiful part of the crystal? Yes.
What other parts?
These other parts.
Okay, so that was the point of making the distinction between this and pretty much everything I talked about after this slide. Okay, so that these guys here are definitely the result of this kind of instability.
Yes.
And the reason they are is because ultimately, after some time period, this thing gets big enough that so imagine the diffusion field around this, circular, say, for a circle. Okay, but now the diffusion field I can't draw hexagons. Let me draw a square. Okay, where's the gradient highest?
Gradient. Yeah, on the corner.
Precisely. So once the size of the system becomes big enough that it starts to see these differences between here and there in the diffusion field, then the polygonal shape gives way to this instability, which is based on the diffusion field.
Yeah.
Okay, and so when it gets big enough, it starts to feel the diffusion field, and then the polygon breaks down into this dendrite, and so that's like this instability. And so one of the main groups of people who historically worked on this, instead of doing this and recognizing that when the system is small, it must go through polygonalization. What they did was to say, so what I claim is that my shapes, which are partially rough, become squares. Okay. What they would claim is that you begin with a circle, and that the circle becomes unstable to some fourfold perturbation, which they impose on the problem here. Okay, and that's what people have done. And then so when years ago, Eshel Ben Yaakov, who was one of the people who did this, was in my talk, and he didn't say anything because I can always revert to the observation. Okay. Now, this one too I can explain, because this one is an initial condition above the roughening transition, so it is a circle. Right? So this one is absolutely a circle, and it goes unstable. And look at that pattern. It's not got six-fold symmetry. It's got sub-six-fold symmetry. The facets start to come out, but they still have a bunch of fingers on each one of the facets. So then there's a nonlinear selection mechanism, which has to do with diffusive screening. Right? So once the thing goes unstable, now I've got this looking into the diffusion field. If this one grows a little faster than this one, it grows a little faster, and it screens its neighbors. Okay? From further diffusion field. Right? That's through this condition. This says that the local velocity depends on the flux. Okay? So if I can have the local velocity fluctuate just a little bit, then this one reaches farther into the source material than this, compresses the diffusion field a little bit more than its neighbors do, and then wins out.
So how is this described by nonlinearity in the diffusion coefficient, or?
No, you either have to solve the full equations in their great glory, which is not easy to do.
So it's not a diffusion equation then, yeah?
Right, yeah, the full diffusion equations for a moving boundary.
Okay, so it's still the
so it's still so the field equations don't change. The rub in all these problems is that on the face value, this parabolic equation only has two boundary conditions. Okay, but what you have to realize is that you need a necessary condition to move the interface, which is this condition, the Stefan condition, and in addition to that, the surface is evolving, therefore its curvature is evolving all of the time. Okay, so this boundary condition itself requires the solution to the problem to impose. And so I would also say that the linear mode is subcritical for this problem as well. And so the Landau coefficient is hugely negative and of high magnitude. So if you do mode expansions on this.
For the fingering problem, you mean?
Yeah, just for the linear stability. When you analyze this using the amplitude approach, then you find that it's highly subcritical.
By highly, you mean there's many amplitudes which are.
I mean two things. I mean two things.
6 or 8.
One is that the magnitude of the Landau coefficient is huge.
Yeah.
Okay. So that's important, just for the mode
The
expansion.
destabilizing one, you mean?
Yes, the destabilizing one.
The second order.
The second, the one which is A mod A cubed. That thing is minus Landau coefficient A mod A squared. Sorry. The size of that is huge. Okay, I mean it's just a fact, right? So if you just do, so that's the most dangerous mode. If you do the expansion of that about itself, then you get this result. Okay. However, if you go further and look at epsilon on either side of this and do a troika of modes, you find weak wavelength selection. Okay, so you have a subcritical bifurcation and a very, very flat neutral stability diagram. Okay, and you can reason it in the following way. Most in problems like Saffman-Taylor, where I also have a competition between diffusion and surface energy, but not surface energy as a function of orientation, surface tension instead. It turns out that this mode is fairly well selected as long as there's not a finite geometry, because these two length scales are not too disparate for that system. Okay, for fluid systems, it turns out that these two are disparate. Okay, this might be 10 nanometers, and this could be millimeters or 10 millimeters. So qualitatively, the competition is between a very short length scale stabilization effect and a very long length scale diffusion effect, right? And so that gives you, at least when the mode starts to go unstable, a whole range of, you know, they're about the same size, okay, in this experiment. But the ultimate thing that manifests itself, I think, as Ito was getting at, is probably that there's a bunch of other stuff that happens that you don't see. Because ultimately this crystal will look a lot different than this crystal. And that's forgetting the important aspects of three-dimensionality. You know, I mean, Yoshi's measured the three-dimensional structure of these crystals, and the three-dimensional structure is, unfortunately, he made these measurements because it means that these kind of models are metaphors and less predictors than they are metaphors, because the third dimension can become important as the instability evolves, which actually I haven't really obviously kept up with what people are doing. You know, we understand the instability. We understand the nature of the instability. Could we control this shape? I would say probably not right now. In any system, certainly you would like to control it in metals, but you can't see them. But we do understand, I think, this transition to a polygonal shape, at least in the laboratory and theoretically. That's mostly what I was getting at, and it depends on simple concepts of how molecules make their way onto the surface, diffuse on the surface, and incorporate themselves into the lattice.
So details about the shape will then all be described with this gamma function, is that right?
Related to the gamma function, but really this V tilde for the polygonalization. And then, yeah, so we begin with the shape that is determined by gamma, and then we make sure that our disequilibrium is small. So as I told someone, it's the normalized delta mu on KT in these experiments of Minoru's is 10 to the minus 7. So it's a part in a million deviation from equilibrium. So it's very close to equilibrium, very slow growth.
When you say 10 to the minus 7, you mean delta mu divided by mu?
No, delta mu on KT. Sorry.
Oh, divided by KT.
Just the dimensionless growth drive. Yeah. I mean, of course, it matters because you're moving along to lower temperatures, and you go, like 16 degrees to lower temperatures. But it's still, I think the point is that in that apparatus, Monoro can control the delta mu very accurately. It really is a big wheel. It's quite impressive. So he has this huge Bourgeon gauge, and this looks like a boat captain's wheel. And because of the way it's rectified, he can just move it, this much, and it's a tiny change in the pressure. And I would say all of this should not be taken quantitatively. That's why it looks like a scanned-in version of Monoro's experiments, because I scanned it in. It's not published, and the reason he wouldn't stand by this as being something for research, except for just interesting pictures, is that that it's grown, in 8 seconds. Okay. So the diffusion field becomes really important, and so the finite size of the system. So he's not getting the heat out. So there's heat building up, and it's sort of very, but they're nice pictures.
I have some kind of vague question about the growth of an ice crystal in later, like the blue curve that you have drawn there.
Yeah.
I can understand how the water molecules are incorporated on the rough surfaces, but what do you think happens with the water molecules ending adsorbing on the planes? Can you talk about some kind of efficient uptake coefficient? They will stay. They try to diffuse a little bit. And
okay, so we thought a fair amount about that. So all I've shown you were a bunch of velocity functions, but so you're talking about these orientations here.
Water molecules landing on that.
Right. So the way so there is a lot of work done on how these kinds of things grow, and so the basic idea is more or less what you showed in your simulations, that there is birth and spreading. Okay. Now, importantly, the secondary processes. So imagine, this is my facet, and I have material raining down on the surface. It has options, as you pointed out. It could find another add molecule and create a binary, and then another one, and so forth. Okay? But there's a critical size. Okay? So it's just lower dimensional nucleation theory. There's a critical size below which it will desorb, and above which it will grow. Okay? Now the other thing we know is that, so an island, so if I'm looking down on an island, if this is beyond the critical value, it's going to gather all the molecules that are in some region of it and grow. Okay? So, importantly, in one dimension, all phase boundaries are molecularly rough. So that is, the melting temperature in one dimension is 0 plus epsilon. Okay? You'll have to take my word for it. So this is molecularly rough, so there's no attachment there for a molecule to make its way onto this surface. So that means if it comes, it's going to grow. Now there's a depletion layer, okay, and many things can happen. Now the delta mu on KT being 10 to the minus 7, we know that for most systems, since that's the normalized growth drive, that we're really in the single birth and spreading regime. So that I'm at delta mu greater than the value for critical nucleation, okay, at less than the value such that more material comes onto the surface before this spreads and completes a monolayer over to the Bismarck regions. So we know that up to an entropic cofactor. Okay, but people have even measured that for metals, for example. No one's measured it for ice. Okay. But those are scaled out of the system. Okay, there's 2 cofactors scaled out of the system, and so so we know we're in that regime. That's birth and spreading. There can be kinetic roughening, which means that because the material rains down so fast on this surface, it actually, before an island moves a diffusion distance, another island forms on top of it. Okay, and then it becomes kinetically rough. And that's at a delta mu on KT about 4 orders of magnitude larger. Okay, so for our purposes, the important thing is that the velocity normal here is enormously small relative to the velocity normal here. So actually on an optical scale, you don't even see the facet moving on a time scale by which the corners grow out. But you know it does move because when you melt it back and grow it back, it's not precisely the same place all the time.
It's related to what people do when they measure uptake coefficients that are very small to water and ice particles in the atmosphere. They say that the sticking coefficient that they call it then to be less than 1%. That's
I
wonder how that's connected to what we're talking about.
Yeah, I have a lot of trouble understanding these things. I've always had trouble understanding the idea of the. I mean, sticking coefficient, as a matter of principle, I understand, right? Say, well, it's the probability that if an add molecule comes, it will stay.
It's always a time scale involved. It will stay there for the time that you're measuring, or
yeah, and then
that makes the definition problematic.
so I haven't understood it. I'll just say that.
Yeah.
Whereas here, I could translate, for example, our velocity function into something related to a sticking coefficient. But I think the important thing is, in the atmospheric setting, people are still thinking about, they think about it like this all the time. Namely, you have like mass growth instead of even the, what they do is they, I mean, this is Marcia Baker and John Nelson. So what they do is they say that d by dt of the mass is related to the flux. And then they, after the fact, they impose the shape which is self-consistent with a mass evolution. And the tuning parameter for that is a sticking probability or a condensation coefficient or whatever you want to call it, but something like that. And I view this problem as, in fact, rather different. That is that the goal of crystal growth is to predict the shape, not specify the shape which is consistent with the amount of mass, because I know, for example, I can immediately show you that the equilibrium shape is in the same shape at all temperatures independent of the volume.
The lab experiments on ice particle growth says to vary within a factor of 100 or so, and it's trying to extrapolate that to what happens in clouds within the atmosphere. The difference in growth rate of cloud particles is a factor of 100. That's huge effects. So it's a important problem actually.
Yeah. So I mean, well, one of the things that I would argue is that if you were to properly separate regimes, you could deal with one size distribution using our simple approach, or a fully three-dimensional version of our simple approach, and say, you know, if I know what the mean free path is in the vapor, I can tell you this is the type of growth model to use, and it's pretty simple. You know, you could just evolve the curvature of these particles, and then you would say, well, there's going to be a muddy regime, which is the regime between that and this diffusive growth. But I know sufficiently little about it that I would say I would be concerned, because as a parcel of air is moving through, for example, a cloud, you know, there may be places where it's moving monotonically up, but accelerating. It might be going at constant velocity. It might be oscillating, like it is in the high atmosphere. And unfortunately, that makes it beyond the scope of my ability.
I have another question also about the crystal growth. What about the post-liquid layer? Does it influence these processes in some way?
Yeah. So, in fact, very centrally, we think in this 2-page paper that Yoshi and I wrote in Physics Today, we sort of outline it in, so the quasi-liquid layer, and so this is the other part of Andy Cahoon's thesis, is, I could show you, so we model that, so let's put a quasi-liquid layer on there, okay? So now we model that. I don't know if you're familiar with Ginsburg-Landau Model B or Kahn-Hilliard theory, but we model these things, and we ask ourselves for what delta mu's, so if delta mu goes to 0 for a flat interface, then we have the equilibrium quasi-liquid layer. And now let's turn on some delta mu, and we predict what happens to the thickness of this layer. And you find that the thickness changes. So that's certainly important, because if it's very thin, then you can imagine, it's within a molecular layer of the surface, then the kinetics of that surface might not be that much different than just the dry, nearly dry surface. But now, let's make it get thicker. Okay? So the way in which I make it get thicker is important, because we know from this that, okay, this is solid liquid coexistence, right? And below here, at temperatures below this, I have a faceted prism plane, okay? And above this, there's a rounded prism plane, so there's a roughening transition. Now I'll just tell you two important things. The roughening temperature for the basal plane is the melting temperature against the ice, against water. It's the melting temperature. Okay? The roughening temperature for the prism orientation is minus 16 degrees and about 165 megapascals. Okay? So now I'm at atmospheric pressure, and I'm going to grow my crystal. Okay? I've got a quasi-liquid layer on this prism, okay, and I've got a quasi-liquid layer on the other orientation, say. As the layer thickens due to disequilibrium, if there's enough water such that, and what do I mean by enough water? If the layers stick relative to the correlation length of the two interfaces, then it's bulk. Okay? Now, if it's on a prism orientation, importantly, the prism orientation maintains itself in vapor to very high temperatures. In disequilibrium, if there's a thin liquid layer that thickens, then poof, the roughening transition down here will onset. Okay, so that's really, this beautiful ice crystal that we have here. This thing, right? This is in vapor or air. All right. So you see the prism orientations, but if you drive the system hard enough and create a thick liquid layer, and you're down at these temperatures, or up at these temperatures and pressures, and you thicken the layer on the prism facet, then it looks like bulk water, and then it will roughen. And then you should get a dramatic change in the growth rate. Now, so that's the idea, and we haven't, actually we have good evidence that the change in the thickness can become thick relative to the correlation length using these theoretical approaches. But those theoretical approaches don't have how the interface itself may change. So we just know empirically that there's a roughening transition. But it's just, in the theory, it's just a phase boundary. So the theory is thermodynamic and not microscopic. So you need another ingredient, which is really experiment. And one would imagine that you get these abrupt changes. But I think the important thing is to leading order, forgetting all that subtlety. If there's a liquid there, then there's going to be a difference between the sticking probability on that liquid, quasi-liquid surface.
When you talk about shocks, you really just mean the
Corners.
faces, yeah?
Yeah.
The corners. of the faces?
Yeah, so we have so there are losses and orientations. So what I mean by shock is that
Maybe you can draw this.
I just have pictures of it here. So I have all these orientations, theta, okay, and I solve this equation using characteristics,
Right.
okay, and so the point is that there can be two. So the shape at any time is just simply a line, okay. The magnitude of that line is this thing, okay, and so you see there it is, and there it is, and these two can collide.
Yes.
Right? And when they collide, where are they coming from? They're coming from, a place with some orientation, another place with another orientation. So all those orientations that were between them are lost.
Yes.
And so that's what I mean by a shock. And it means that two characteristics intersect.
Yes. Yes.
Yeah. So that's all I mean.
And I mean, normally, if you didn't have any, I mean, there is an issue perhaps with loss of uniqueness, which of course you don't have. So why exactly do you not have a loss of uniqueness?
Okay, so we know the orientations for both of the characteristics that collide. Okay, and then at that point, I update the surface. Okay, and I've just lost all those orientations. So I have all the orientations that I have for all times that are evolving, and I can have as many shocks as I want. Since I know all the orientations they come from, then the next point, I have a corner, and I can perfectly well live with a corner. It's fine. And I could have another shock, and then I lose those orientations, and so forth. So there's no issue of uniqueness because I only have all the orientations I have, but they've been knocked down by some factor each time I have a shock.
If you were to go backwards, of course, you wouldn't be able to do that. I wonder whether that's...
Oh, you do. In fact, you lose orientations on the surface when you go backwards as well, when you melt the crystal. So that was, so for example, you can see these subplanes that grow in here, right? And then eventually you have, again, 6 sides, okay? But there's a little curvature to all of these things, okay? And then you grow it again, and you come back to this facet shape with, that orientation, that orientation, that orientation, that orientation, that one, and then these little range of orientations here. And in melting, you do have an interface running off and colliding because the one that can't lose material fast enough is going to be collided with by the stuff that can get rid of material, and so you also lose orientations in melting.
But you would not expect really the phase to be stable after multiple melting and remelting. I mean, melting and growth.
So importantly, this is a disequilibrium shape.
Yes.
Okay, very much so. I mean, that's how I first got into this business, was that there was a conference in, second reason I got into this business, there was a conference in Minoru showed his high pressure results, and he for the roughening transition, and so that's an equilibrium transition, and I asked him, are they equilibrium? Because I had been thinking about equilibrium shapes.
Yes.
So he showed these results. And I said, are you sure you're right here? Because it's important. The transition, he says, is right here, and that is that this facet roughens, okay, and he said, I'm not sure if I'm sure. And the reason I said this is because if you're slightly away from equilibrium, then you get these faceted shapes that you might say are equilibrium, and then you would say, oh, the roughening transition is at some other place. So that's how it started. Importantly, your point is really that the disequilibrium shape is not the same as the equilibrium shape. But in order to know how much it deviates, we have to know rigorously what the equilibrium shape is to do the initial value problem. Now everyone's everyone's sick of me talking. And
Okay,
maybe I should have another coffee.
let's all have coffee then.